Today we're going to discuss, extend your work on that you learned from sorting and searching and order statistics a little bit more, and then make something out of it. How many of you are familiar with searching in an array, searching a number, a key in an array? Anybody, please raise your hand, just say something. How many of you are familiar with searching in an array? How many of you can search an element in an array? What is the algorithm to do it? You just go through every, or binary search. One will use linear search, one will use binary search. When the input array is sorted, the search space is sorted. How many of you are TAs here? Anybody who is a TA for the course? Can you please close the doors? Yeah, you, I know. Close all the doors and just don't make noise. Okay, so how many of you are familiar, know sorting? Which sorting algorithms do you know? Quickly, name some sorting algorithms. Bubble sort. Any other sorting algorithm? Can you please not talk to each other? This guy. Don't talk. Any other sorting algorithm? Merge sort. Anyone else? Quickly. Radix sort. That's good. Counting sort. Yes. Quick sort. Anyone else? Anyone? One or two left? Huh? Insertion sort. Yes. Heap sort. Yes. यार पढ़े लिखे लोग हो ऐसे हमें तंग करने आ जाते हो इतना तो मुझे भी नहीं आते seriously I don't know what is heap sort. Well, I know a little bit. Yes, okay. So selection sort nobody mentioned. The basic, the one which gives us the definition of sorting. Selection sort. How many of you know selection sort? All of you know select algorithm, right? The order statistic selection. Select a number of a particular rank, like median or something in an array. If you convert it into a sorting algorithm, you can just repeatedly find min of the remaining arrays and place it in the location, and that will give you the sorting algorithm that's called selection sort. Find min and place it at the first place. Then find min of the remaining and place it at the second place, right? In the output, find the min of the remaining and place it at the third place. And if you continue this n times, you will get the sorted array, okay? Okay, so today we are not going to have any of poll EV or that Slack or any of that nonsense. So please don't use your phones, okay? Please do not use your phones in the class. You are allowed to go outside if you really think something really, really important is coming up. Allowed to go outside, save the world, come back. But when you are in class, try not to use any electronic devices, okay? And especially don't try to hide it from me because I have a different viewpoint. I can see a lot. So don't do this. Okay, so let's just do this simple problem, extending your knowledge. Apparently you know quite a lot. So finding the ranks of an element, okay? So we define the rank of something. I have a habit of precisely defining stuff. So you're given an array A of numbers, n numbers, integers for now, and the rank of another number x in this array A is denoted, the way I pronounce it is like rank in A of x, okay? The rank in A of x is just simply the number of elements in A that are smaller than x, okay? So it's practically, so you find the subset of elements in A that are smaller than x, and then take the cardinality of that set, and that gives you the rank of x in A. Is this clear? Okay, just quick example. Here's an array. What is the rank of 5? What is the rank of 5 in this array? Say something, please. Why 2? Why is the rank of 5 in A 2? There are two numbers, one is 4, the other is 2, which are smaller than 5. That's why the rank of, what's the rank of 3? Why? Because only the number 2 is smaller than thing. Why wasn't the 5s counted in the rank of 5? There are two 5s, one 4, one 2, right? Then their 4 are smaller, less than or equal to. So if we have a definition of rank is less than or equal to, then we will count it. Otherwise, in this case, for this definition, we won't count. Okay. What is the rank of 1 in this array? What's the rank of 1 in this array? Why? What's the rank of negative 17 in this array? What's the rank of positive 17 in this array? The number of elements. Yes, and how many are those? What will be the rank of the min in an array? Why? Because there is no element that are slightly smaller. What's the rank of max in an array, in this array A? The rank of, what is the rank of the max of A? Everyone knows max of A, right? What will be the rank of the max of A? Size minus 1? Oh yeah, size minus 1 if the rank, if every element appears at most once, if these are distinct elements. But if the max, the number max appears multiple times, then they cannot be counted as numbers that are smaller than the max, right? So it will be rank of A, rank of the max will be the length of A, then n, minus the frequency of max, okay? So I just brought this thing in so that you know that there will be, this definition is not a fixed definition. You have to understand that what some people define rank as the number of elements that are at most x, right? So number of elements less than or equal to x. Sometimes it's defined only if there are distinct numbers, right? So if distinct numbers, then this frequency of max, because the frequency of every number is at most 1, so then in that case it will be n minus 1, okay? Similarly, if it's less than or equal to, the rank of min will be, could be actually 1, right? Or could be the frequency of the min, okay? If this is less than or equal to and there are repeat. Does it make sense? Yes. So it's a simple concept. I worked with integers, I worked with strictly smaller, it could be real numbers, it could be negative numbers, could be anything, right? So, but for now, let's stick to integers and even distinct integers for some time. It makes life easier to talk about the stuff. So now we're going to convert it into, so this was just a concept, just a definition, right? Nothing. Let's convert it into algorithmic problem and see what to do. We are given a sorted array A and a number x, which is an integer. Array is also integer and distinct integers, right? And it is sorted, and we want to find the rank of x in A. Okay, let's start talking. What is the rank? How do you find the rank of x in A? Quickly, yes, go ahead, start talking. Yes.
So we'll compare the number to every other number and then count which are smaller.
Compare which number to which number?
जिसका rank निकालना x.
उसका x नाम रखा है ना, the नाम इसलिए रखता है कि we can talk about it, okay? So it's easier to do. उसका इसका फिर मसला होता है. So what do? You compare every number in A with x.
In the array and then keep a count of the elements for it.
Yes, so this is a very simple linear search algorithm. You go through every element of A and see if it is smaller than x. If it is, then we increment some running counter, and in the end we return the value of that counter. Anybody who has any issue, any objection on this algorithm? Yes?
It's already sorted, just wait for the first element that's bigger and then you count all.
Okay, that's a very good idea, very good thing that we're going to talk about it in a minute. Yes?
Isn't the index the rank in this?
Isn't the index what?
The rank in this array, if it's sorted and it has distinct elements.
But x doesn't have to be in this thing, no? So in the array is n positive integers. So she says, why can't we just essentially do searching, right? You said searching, right? But x doesn't have to be in A, right? So in the previous example also I gave you many numbers. So 5 was in A, but 3 isn't in A, right? 0 isn't in A, negative 10 isn't in A. So, but that's both of these ideas, we'll talk about it in a minute. So, but the algorithm we got was just go to every element and see if they are smaller, count the number of elements in A that are smaller, and then the input x, then that's how we count the rank. But it didn't make use of the fact that the input was sorted, right? It didn't make use of the fact that input was sorted. What do you do rather than linear search? What can we do to find the rank of x in A if we know A is sorted? Yes. Stop where? Which algorithm stops? The same linear search algorithm? Okay, that's good. There was another proposal already that we can do linear search, but the moment we find a number that is greater than or equal to or bigger than x, then we can just say stop. Yes? So the linear search, it's actually exploiting the fact that the array is sorted to some extent, and it gives us this algorithm. So we got two proposals. Yes, binary search and what? What else? We need to. Sorry? Binary search से कौन सा value निकालें? What if it's not there? We don't know if it is going to be there. No? Okay, good. No, n to khair, yes, we'll see. Okay, so that's the thing. We were counting the number of elements that are smaller. We don't have to just report them. We don't have to output them, right? So that's why there's no point in putting them into another array or something. Sorry? Yes, so that's what we are going to do. Go through every element because they are sorted. And as soon as we find a number that is bigger than or equal to x, we stop the search and we return how many steps did we take. Right? Yes? Okay. Yeah. So that's a very good idea that we are going to do. So just do a little bit more bookkeeping, a little bit more detailed observation of binary search. When binary search fails, if it succeeds to find the number x, then we know exactly, right? These are distinct integer. If x is in the sorted array, if x is at index 10, what is the rank of x in A? So A is sorted numbers, x is part of A at index 10. Then what will be the rank of x in A? 9. The left 9 number, the previous 9 numbers were smaller than x, right? So the rank of A. But if x is not there, then we can do something like this, right? So this, I'm sure you have heard this word, the external binary search. It's a binary search, but the requirements are slightly more than what is the usual thing. Find a number, and if it's not found, then return not found, return -1, right? It's not that. It's just that you either find the number x in the array, in the sorted array, or you find the index where x would have been, right? So you find the index of the largest smaller number than x, or the smallest bigger number than x, right? So the one that would be just the right of x, or the one that would be just to the left of x if x was there. Does it make sense? It's not very difficult to see. It's exactly the same algorithm. You do binary search, the prune and search technique. You find the middle, you compare that number with x. If it's bigger, you start searching in the left array, subarray, half. And if it's smaller, then you repeat the search in the right subarray, and that's exactly the search thing. The time when it stops, at that time you will either have x at that current middle, or you will have a number that will be either the bigger one or the smaller one. Okay, that's simple thing. Just rather than just returning not found, it's a very good exercise to go home and spend like 2 minutes on it and try to write the details pseudocode of external binary search, which returns the index of the next element from x when it's not found in x. Yes, when it's.
If x is at index 10 corresponding, there are 10 elements smaller.
No, there are 9 elements smaller because x is at 10. Nah? So the 10. I don't know. So you start index from 0 or 1. That's just a convention. I generally we start indices from 1. So you're thinking of index start from 0, right? Okay, so that's a C++ kind of notation. I start index with 1. Okay, but those are kind of notational conveniences. Just do it. I like it. Counting everything is easier for me if I do this thing, right? So make sense? Typically, math people start it from 1. Computer science idiots start it from 0. Okay. So generally, I tell jokes about business school people, nah? But now I'm here, and this is going to be what's called namak harami in Urdu. So I don't want to talk about business school people, and there may be some spies here. Are there any spies from business school? No? Good. Okay. So finding rank the problem is clear. Everybody, the problem is clear. Yes, how to find rank. So we will do extended binary search, finding the rank of anything. How long does it take binary search? It's exactly the same number of comparison as binary search takes, because there is some extra bookkeeping at the end. Rather than returning -1, you return where the search stopped, and that doesn't count. There's no comparison there, right? So it's still log n comparison, and if you're not happy with it, just call it order log n comparison. Is this clear? In log n comparison, we will find the rank of x in A. Okay? But the previous idea, we will continue this thing. It's not a very good idea, that the linear search idea, the linear scan idea. We scan the array elements in A and one by one from left to right, and we return count the number of elements that are smaller than x. Right? In the worst case, this could be, by the way, order n, right? If some of you suggested, what if we stop searching the first time we find a number bigger than x? So that's a good idea. It will work, but in the worst case, every number could be smaller than x, and it will have to go through we'll have to complete the scan. Make sense? Anybody who has any issue with this thing so far, with these two algorithms and their run times? Everybody is convinced that both these algorithms are correct. Everybody is convinced about their runtime, their number of operations. Anybody who has any objection, any issue? Which one of the two is better? Which one of the two algorithm is better? The first one, right? Why? Because it takes log n comparison, and the other one takes n comparison, and for any positive number, log n is smaller than n, right? In the worst case. But let's just extend the problem. I am now going to do, we are given the same sorted array A, which has n distinct integers, but now we are given 2 integers. Rather than 1x, now we are given x1 and x2. And we also know that x1 and x2 themselves are sorted, or x1 is smaller than x2. And we want to find the rank of both x1 and x2. Make sense? The question clear? The problem clear to everyone? We are going to find the rank of x1 and x2 in a sorted array A of n numbers, and we know that x1 is smaller than x2. Do you guys feel this in your eye? Good. Good thing you feel it, because otherwise, if you see anybody who doesn't feel it, and I take off my shoe and throw it at them. People who use cell phones in my class. So, laugh it once in a while, okay? Just don't take life so seriously. Definitely, you don't take the course that seriously. We want to find the rank of x1 and x2. We can exploit the fact that the array A is sorted. We can also exploit the fact that x1 and x2 are given in some order, right? Or we know x1 is smaller than x2. Okay, what is the dumbest way to solve this problem? Quickly. Not the smartest way, the dumbest way. Yeah.
Do a linear search, each x1 and then compare linear search again.
Okay, so he said we do a linear search to find the rank of x1, and then we do a linear search to find the rank of x2. What will be the runtime? N? Seriously? N was the previous one. I didn't use the word order, right? So this was n. You see, n comparison for rank of x1. N squared? n squared. What will be, so here is the thing, n plus n. I have to say the fancy word of n squared or n2n or something. We do it once for x1, it takes n comparison. You do it another times for x2, it takes another n comparison. So it takes n plus n, which is equal to 2n, right? Not n squared. Okay? Think simple, okay? I'm a very, very simple person. So choti baatein karta hu, bade words na use kiya karo. Okay, stop the phones. But there were two algorithms on the previous slide, right? So we are building upon the previous one. That one was the second. What if I do the binary search twice? We have two recipes to solve the problem for x1 or x2. What if I repeat both, either of them for x1 and then x2? What will it have? Why can't I do two extended binary searches, once for x1 and once for x2? What will be the runtime of that algorithm? Somebody. What will be the runtime of that algorithm if I do one extended binary search for x1 and another for x2? Say something. Yes, they told. You don't want to talk to me? This is not a big deal if I ask you. Even if I ask him, you can answer. Right? You can, yes, please. Log n plus log n. One log n extended binary search for x1, one extended binary search for x2. Right? Here we can use some tricks there. We can exploit the sortedness of x of a even further. Right? The second one doesn't exploit the sortedness of x. This first algorithm does. The binary search one does. What can we do here? Suppose I know that the rank of x1 is t. So let's say it's 19. Rank of x1 is 19. Then my effective search space for the rank of x2 is array from 19 to n, right? 19 plus 1 to n. Does that make sense? Yes, I only have to start looking at it. So if the rank of x1 in A is t that I found through the first binary search, then the next binary search I can do only from the subarray that starts from t plus 1 and end at n, right? So the next binary search can take this array AT to n, and that is AT to n, that if I do binary search, then it will take log of the length of the array. The length of the array is n minus t, right? So it will be log of n minus t, which could be slightly smaller than log of n, depending on what's the value of t. But in the worst case, t value could be 0. Right? X could be negative infinity, x1 could be negative infinity, and you didn't gain anything from this optimization. Does that make sense? So that's, but I just wanted to throw this thing at you that technically in some cases you may be able to do better if you just exploit the fact that x1 is bigger than x2, x1 is smaller than x2. Okay? But in the worst case it will take 2 log n times. What if I do 2 linear searches? What if I do 2 linear searches? That will be one linear search takes n times. The other linear search to find the rank of x2 also take n times, and that's the runtime is going to be 2n. Is this clear? What is going to be the next slide? Quickly. What is going to be the next slide? Yes? The first t numbers, yes. Yeah, that's coming in the next slide. But just tell me what will be the next slide. What will be the problem on next slide? Compute the rank of 3 numbers, even simpler, right? So now we've computed the rank of 1 number, then the 2 number, then it will be the rank of 3 numbers. x1, x2, x3, we know x1 is smaller than x2, x2 is smaller than x3, or we can just sort them, right? We can just do a couple of comparisons to do that sorting. Okay, now solutions. What can we do? We can use the previous slides, right? What will be the first solution slide was finding the rank of x1. We can just use that slide to find the rank of x1. We have 2 algorithms. One takes log n comparison, the other takes n comparison in the worst case. If I repeat that algorithm for those 2 algorithms for x2, I'll get one which solves the problem for x1 and x2, 2 log n, and the other which solve the problem for x1 and x2 in 2n times. Then I can repeat it another time, and I'll get an algorithm which solves the problems in either 3 log n comparisons, or the other algorithm, we can solve the problem in 3n comparison. Got it? Yes? Anybody who is not happy with this? No? Everybody is happy? What will be the next slide? Huh? 4 numbers. Yeah, grow up a little bit. I mean, come on. Just let's go directly to n numbers, okay? Now, this is not actually the next problem. It is the summary of the previous 3 problems, and this any number, because n could be 1, could be 2, could be 3. Is this clear? How many algorithms do we have to find ranks of numbers? We have 2 algorithms. One is repeated binary search, the other is repeated linear scan, right? Is this clear? What will be the runtime if I use repeated binary search? What will be the runtime if I use repeated binary search? How many times do I have to repeat binary search? N times. For each of the numbers x1, x2, x3, I have to do extended binary search, and that will, each one takes log n times, so the total time will be n times log n, right? If I do linear scan, repeated linear scan for every xi, stop this thing, what will be the runtime? Each linear scan takes n times. If I do it n times, if I repeat it for n xi's, then it will take n times n, which is n squared time. Okay? Make sense? Now let's come to the initial idea we got, that why the second linear scan algorithm is essentially not exploiting the fact that the array A is sorted. Okay? So we are going to begin exploiting that. Okay. So is this clear? Is this n squared algorithm clear to everyone? Okay. So this is the following thing that suppose I know the rank of xi, or let's say x1, the rank of x1 is t, right? So the first t numbers in this array are smaller than x1. Okay, the first t numbers are smaller than x1. Then can I say that they are already smaller than x2? Why? Why can I say that? Because x1 is smaller than x2. उल्टा लिखा हुआ है. No, x1 is smaller than x2. Okay? So any number that is smaller than x1 is already smaller than x2. So if I know t of these a numbers, m numbers in A are smaller than x1, then they are definitely smaller than x2. So when I'm computing the rank of x2, I could just start from that t. So I could just see, is the t plus first number smaller or bigger than x2? Is the t plus 2 number smaller or bigger than x2? I don't have to compare the first x1, the first 1 to t numbers. Is this clear? Yes? So look at this picture. All these numbers, because I know the rank of xi, now this is just any number xi, the rank of xi is t. So all these numbers in orange, they are smaller than xi. Now they are already smaller than xi plus 1 also. Okay? So I need to compare, to find the rank of xi plus 1, I only need to see the green region and see how many numbers here are smaller than xi plus 1. So suppose 10 numbers in the green region are smaller than xi plus 1, then what will be the rank of xi plus 1? 10 numbers in the green region are smaller than xi plus 1. What will be the rank of xi plus 1? 10 minus? 10 plus 1? Why 1? So 10 numbers in the green region, look at the pictures, 10 numbers in the green region are smaller than xi plus 1. What will be the rank of xi plus 1? 10 plus? 10 plus t, why?
The orange array we have, there are t, the rank of xi is t, and the number of, like the cardinality of the number is smaller than xi are t. So t plus, there are
Good. Yeah. So 10 numbers in the green region are smaller than xi plus 1. How many in the orange region are smaller than xi plus 1? How many in the orange region are smaller than xi plus 1? T, all of them. Why? Because we know they are smaller than xi, which is smaller than xi plus 1, so they are already smaller than xi plus 1. Does that make sense? Please understand this thing. This was the initial idea given by two people at least, that if we found the rank of xi for or any number x, let's say xi, which is t, then the rank of xi plus 1 is going to be greater than or equal to t. And how much greater? That you need to go to the green region and find how many of them are smaller than that, right? So once the first time we find a number bigger than xi, then only that number onward numbers need to be compared with xi plus 1, with the next one. Is this clear? Anybody who has any issue, any objection, any question, any comment on this? Yes, please go ahead. Sorry, please say it again. Which list? The array is? GG. Good. That's a good thing. Very good observation. It's actually somewhat correct observation, but you're not pronouncing the right words. Okay? I don't know if you did discrete math with me or used my slide. I take words very, very seriously. Okay? Rank is not a thing. Rank requires two things. Rank of what in where. Okay? So when we say the minimum of an array has rank 1 or 0, that means this min, the element min, has rank in this array where it is contained in that array it has rank 0, right? So this is true that the sorted array A is given in the rank order, whatever you call it. It's a proper order. The rank 0 element is at the first index, rank 1 element is at the second index, rank 3 element. But now we are looking of the rank of x. These are something external to A. Okay, some other number, they may be actually also found in A, but we're finding the rank of x's in A. Is it clear? No? You look very unhappy.
I'm a little confused because I was thinking once we found out the rank of x1, we know that there are n x's, right? So we know that there are n elements, and we know each of them must have a corresponding element that's like an additional element that's smaller. So we could just add 1 to the previous rank. I don't know.
No, so let me just make an example here. So give me numbers which are sorted, okay? Give me sorted number. Well, that's a good chalk. I think that's okay. Give me numbers that are sorted. Give me sorted numbers quickly. Okay. Okay. So what's the rank of 11? This is my array A. Let's call it A. What's the rank in A for 11? Quickly. What's the rank of in A? What's the rank of 11 in A? 3. 8, 9, 10. 3 elements that are smaller than 11. Right? What's the rank of 12 in what's the rank of 12? Still 3, right? What's the rank of 19? So we know that the rank of 12 in A will be bigger than the rank of 11 in A. We know that the rank of 19 in A will be bigger than the rank of 12 and the rank of 11, but how much bigger we don't know. It depends on how many numbers are there between 11 and 12 or between 19 and 12 and something. But the idea there was that if I know that there are 3 numbers, this is sorted. When I know there are 3 numbers that are smaller than 11, In a sorted array, do I know which 3 numbers are smaller than 11? Which 3? The first 3, right? So is this clear? If the first 3 are smaller than 11, then they must also be smaller than 12. Yes? So in order to find the rank of 12, I don't need to see the first 3. I need to compare the 4th, 5th, 6th, 7th. They are potentially smaller than 12. But is this clear? So that was the idea here. The green one, what is it called? The orange and the green ones. Those numbers that we know for sure are smaller than xi plus 1. And the green ones we don't know for sure they are smaller than. So we need to search. Is this make sense? Does it make sense or no? This is the final thing. We are done with finding ranks, okay, for all numbers. Yes. So if I do it for n numbers, my claim is it will in total it will take 2 n comparisons to find the rank of all of these n numbers. Anybody who has any objection, any issue with this, please say it. Yes.
Why 2n?
Okay, why not? So let's just rephrase your question. Why not bigger than 2n or why not smaller than 2n?
I think it means why not n?
Why not n? That's a good idea. Good. That's a good thing. That why not n? But could it be less than n? Let's say it can't be less than n, right? Because for one number, in the worst case, it will take n comparison for one x1 only, right? In the worst case, it cannot be less than 2. Should the other numbers add to the complexity somewhat? That's a philosophical answer. This should be slightly more than n. Here is the thing. You found a number that is bigger than x1. You found a number that is bigger than x1, which will be the first green one, let's say. The first green one is the first one bigger than x1. We know for sure about, for the x2, we know for sure about the orange one. They are going to be smaller than x2. They are going to be smaller than x2 also because, but the first green one, we don't know whether it's going to be smaller or bigger than x2 or equal. Does that make sense? The first green one, I know is bigger than x1, but I don't know whether it's bigger than x2 or not. So I need to compare it again with x2. The orange one I don't need to compare with x1, x2. Does this make sense? For every time you find that t magical number, the t plus first number, you are not sure whether it's bigger than the next x or no. Okay, just slight subtlety, no big deal. As long as you know this no way closer to the n squared thing that we saw in the rough analysis here, n squared, this idea of not repeating something that we already know is going to be smaller than xi, so that saves us a huge amount of time. Okay? Any other issues? Please say it again. Please speak up. Any other issue? Yes, please go ahead. Sorry, please speak louder. We are ignoring t numbers. Yes? With xi, the next xi plus. So what do you think? Should it be bigger than 2n or smaller than 2n? Huh? Bigger than 2n, that's a good idea. Good. Any other issue? Stop the phone, please. Quickly. What's you have any issue with the 2n thing? What do you think should be the number of comparison here? Those 3 people, please. The one who had phone in hand. Yes, sir. Say something, please. Just mark your presence in the class. Say something. It's okay if you don't get it right. Okay. The first time I'm teaching a course, so I only taught courses in SSE. It's the first time I'm teaching a course in business school. This is called Business Data Management course, right? So this is my really first interaction with this species. are really good at, it's a CP thing, right? I really love the class arrangement. It's just very interactive. You just do all kind of discussion, and everybody has an opinion of something, right? And so actually, I never thought I would ever like anything about this what is it they call species or whatever this thing. But this one aspect actually I liked a lot about them, right? So, and I like class to be very interactive. That's why I want people not to use phones and talk to me rather. But do just mark your CP to see once in a while. There's nothing wrong with saying wrong thing. Oh, you're a business school student? Anybody from business school here? All humans? All CSE students, SSE students, right? How can I don't? I'm scared a little bit, so. Shouldn't it be n comparison? Okay. So n less than n, bigger than n. अब बंदा क्या करे यार? Can you call this idiots? Look at me. What should be the number of comparison? No, don't look there. The one who was using phone. Yes, I'm talking to you. Were you also using phone? No, okay. Yeah. Stay in the class. Don't use phone. Okay. Okay. So I'm going to prove to you that it's going to be 2n comparison. There are multiple ways to look at it, right? One way is to see how many comparisons did we do for x1, for xi, for a given x, how many comparisons did we do? It's going to be difficult. It depends on what was the rank of the previous number or something like this, right? What was the rank of the previous number? If it was t, then we'll do t plus 7 or t plus 5. It depends on the value of t or something. So, but if you look at it this way, once you do a comparison of a number in A, some number is compared with any x, what happens? We either move forward and that number is then never compared because somehow it's added to the orange region, right? It's not compared ever again for any other xi's, okay? Or if it's okay, I'll get it for you. If you get a number, see, think of a number aj. If aj is compared with some xi, if it's smaller, then things move to the right, and then all the remaining x's, including this current x, will be compared with something in the right. But if it's bigger, then what happens? We eliminate at least one xi. The current x with which it was compared, that is eliminated again. It will never be. Does it make sense? So if I have the current aj, which is, let's say, bigger than x7, this is bigger, so x7 search is finished. Okay? It will go out, then we'll talk about x8 in x9. So either way, I will either move the a pointer to the right, or I will move the x pointer to the right. Okay? The exact precise code is going to come in the next slide. Let's see if you understand that thing. Okay. Look at the first loop. So initially, this is the running rank. It will every time this r is a rank. It's a number going from 0 to n, right? And it will become the rank of the current element at any time when I'm returning it. It will become the rank of the current element. Okay. So look at the first loop. How many iterations the first loop takes? The first for loop. There is only one loop actually. How many iterations? How many iterations? N? Actually, this is going to be potentially 2n or 2n minus 1, because at some point we also reverse the loop counter. We decrement the loop counter once. Okay? So think of again this thing. When this if is going on, we are just making the orange region, right? We are just extending the orange region. The moment we hit the green number, that green number needs to be compared again with the next x. Okay? And now you see what is the maximum number of decrements possible. In the worst case, for every x, I will do a decrement. So that will be just another n. One is this for loop n, and one is the other. At most, I'll do n decrements. Okay. Seriously, it is no big deal. Every one of you have done enough programming, much more than me, much more, you know, much more programming than myself. You should understand, you should be able to understand this code. It's a very, very simple concept, okay? The best to do is to take a small array of 7 numbers and another array of 7 numbers sorted and find the rank of each number by hand. Just run this dry run of this code, you will see this thing. Is this clear? Yes. 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 Is it clear to you? Okay. Any question with this? So in the worst case, it could be, in the best case, it could be actually less than n. There may be no decrements, but in the worst case, there could be many, many decrements, right? One quickly thing that you should understand, the first time I find a number that is bigger, when I go to the else thing, that time I will return the rank of the current x, and that is whatever the value of r is. Okay? So just technicalities, very simple solution, very simple idea at the abstract level, and now I gave you actually the detailed things, because the theoretical proof is going to be a little difficult. Right? Actually, it's exactly this thing, but this language makes it life easy. The pseudocode language makes life easy. Okay. Let's look at the problem again. Now we're going to black box the solution. The problem was, you're given n numbers. You're given an array of n distinct integers, right, which is sorted, and you're given another array of n distinct integers, because I say strictly saying x1 is strictly less than x2 is strictly less than x3, so these are distinct integers, and I can find the rank of all of x's in A in time 2n. Is this clear? This much black box information, take home message. Find the rank of one sorted array in another sorted array. Can be done in 2n comparison. Yes? Okay, we can do it in 2n comparison, and that's. Now I'm going to do one more problem, and then we'll build upon that something. So this is the algorithm. Okay, here is another problem. It's called merging. All of you should know, because you know merge sort. We are given an array A of n numbers. Again, you can think of them to be distinct integers, but that's just a technicality of writing. Instead of strictly less than, you write less than or equal to or something. Okay, you are given an array of n integers sorted, and another array B of n sorted integers, n integers sorted, and your goal is to compute C, which is the union of A and B, and C is also sorted. Okay, this problem is called the merging problem. Anybody who has any issue with the merging question, the merging problem? Given two sorted array, merge them into a sorted array. If everything is unique, then the length of C will be 2n, right? And if repetitions are not allowed anywhere, so A is totally different than B, A has distinct integer, B has distinct integer, and A intersection B is empty, then A union B will be exactly 2n, right? Is this clear? Can you solve this problem? How many of you can write the code for merging? Anybody who, you must have done it, right? You must have done in your data structure course, in your kindergarten, in your this course maybe. How many of you can you please raise your hand if you can write a code for merging? Okay, please just answer a simple question. How many of you understand the problem of merging? Raise your hand. How many of you don't understand problem of merging? That white shirt girl. You don't know what is merging? You do? So when I asked you to raise hand, you do. Good. How many of you can write the code for merging? Pseudocode or any C++ code or Pashto code or whatever. How many of you can write code for merging? How many of you understand the algorithm for merging? Okay, somebody, okay, you understand. What can you describe briefly the algorithm for merging? Okay, left right क्या होता है? A और B? जी, A और B. हाँ? सी है ना, उसका नाम सी है जी. ओके, सी में क्या कर रहे हैं? Okay, so I'm sure you know the algorithm, and I'm sure you described it the best you can. That's the problem with language. Okay, when in math we always tell, we emphasize keep your language straight, right? So just simple language is too technical, right? So now we have enough vocabulary. It must be related to the previous slides, right? So that's the first hint. The first thing, anytime ever somebody asks you an algorithm, always ask yourself, what's the dumbest way to do it? Okay, understand the problem. Don't jump to solution, and especially don't jump to for loop and while loop and I equals 1, I equals 2 type stuff. Okay, think abstractly, right? Keep your language very, very straight. I'm always interested in the easiest, the dumbest, the brute force type algorithm. Okay, here is the brute force algorithm. You take the union, right? You just dump the array A into some array C and followed by the array B, right? A is there in C and then B is, and then you sort C, right? That will give us, if you sort C, then it will give us a sorted, it will achieve the merging, right? C will be sorted. C will contain A union B because it was made as A union B. What will be the runtime? Well, if we don't know the merge sort algorithm yet, because we are developing the merge sort algorithm, the best algorithm we know so far is all worst cases order n squared. Okay, insertion sort, bubble sort, quick sort, worst case, all of them have have worst case order n squared. So it will take order n squared to merge two arrays, right, by the brute force algorithm, by the first union and then sort. Okay. And the solution that she suggested was basically the following. Here is the thing. Please pay attention to me. Okay, please pay attention to me. Look at this. Here is what she suggested. Most probably that's what she wanted to say. I want to look at it. Which number will come at the first index of C? Which number should come at the first index of C? Quickly. Which one? Could it be A10? Could it be the 10th number in A? Could it be the 19th number in B? Which number will come at the first index of C?
The first element of either.
Either A1 or B1. Which one of them will come? Whichever is smaller, right? Which element will come at C2?
If you pick A1, then either A2 or B1.
Okay, so here is the algorithm that what you wanted to say. The first element of C will be either A1 or B1. Whichever is smaller, you write it and you delete it from the previous one. Okay, the second element of C2 will be either the first in A or the first in the remaining A or the remaining B, right? The updated A, updated B. This is the simple two-pointer algorithm, right? So looking at who should come at this place in C. So looking at it from C side. Let's look at it from A's and B side. Okay? Let's see. I'm asking now from B. Where will B1 go? With which index B1 will go in C? At what index in the final, suppose somebody did merging correctly, where will be B1? Or even simpler question. Who will be to the right, the left of B1 in C, in merged C? Which numbers in merged C, in C, will be to the left of B1? Smaller than what? Smaller where? Smaller? Which smaller?
The ones that are smaller, the smaller elements that are present in A1.
Yeah. The elements in A that are smaller than B1. that will be to the left of B1 in C, right? How many numbers in A are smaller than B1?
At most the entire A.
No. We have a name, not in this particular example. How many numbers in A will be smaller than B1? We have a name for it, right? The rank in A of B1. Okay? Who will be to the left of B2 in C? In C, B2 will be somewhere there, right? The second element of B. Who will be to the left of B2? No who, rank is a number. I'm saying which number will be to the left of B2? One will be B1, yes? Yes, rank is a number. Now I'm saying which numbers will be to the left of B2 in C? Yeah, so which are smaller than B2 in B? Only B1, right? So B1 will be there to the left of B2 and those numbers in A which are smaller than B2. How many numbers in A are smaller than B2? The rank in A of B2. Is this clear? So if you look at it from there, I need to just put in A, B, B1, then B2, then B3, B4 at the right places. The empty places will be filled with A's in that order and that will be merging. Okay? So this is now the algorithm. What will be the index of B1 in C? Give me the number which will be the index of B1 in C. Index starts from 1 in my language. What will be the index of B1 in merged C? It will be a number. Yes, please. 1. 1 to the size of A. So all numbers in A will be smaller than B1? It's possible, but what we have a name for it. No? We can describe it. Not, sorry? Rank in A of B1, rank of B1 in A, that will be the index of B1 or that plus 1 will be the index, right? Suppose rank of B1 in A is 7, so those 7 elements will come to the left of B1 and at the 8th index, the plus first index will be B1. What will be the rank of B2 in A? What will be the rank of B2 in C? Now, what will be the index of B2 in C?
Rank of B2 plus the index of B2 in B.
The index of B2 in B, so that's 2, no? Okay, so the rank of so we know which will be the index of B1 is in C is going to be the rank of B1 in A plus 1, right? Plus 1 is the space it will occupy. What will be the rank index of B2 in C? Will be the rank of B2 in A plus 2. The 2 is one place is going to be occupied by B1. Yes, we are talking about B2. So all those are smaller than in A than B2, they will be to the left and then one B1. What will be the rank of B3 in C? What will be the index of B3 in C? The rank of B3 in A plus 3, right? 2 for B1, B2 and the third will be this thing. Is this clear? So the rank of A in B3 is going to be, the index of B3 in C is going to be rank of B3 in A plus 3. Is this clear? Okay, this is the easier way to look at it because this is the bigger words. I started the session with this thing that I'm always very scared of big words. Merging for me is a very big word. The two-pointer approach is too difficult for me to understand or talk about. But merging is just doing find ranks. Find ranks of B1, then B2, then B3, then B4, right? For each one you find the rank. The moment you get the rank, you do one arithmetic operation, you find the index of B. And once the array is filled with B's, the remaining empty spots can be filled with A's it is, right? In that same order. Okay, we got. What is going to be the runtime of this algorithm? Merging is just finding ranks of n elements in a sorted array of n elements. So it's going to be 2n. So in two n comparisons, we can do merging, right? Once we can do merging, then we can do merge sort. Is very simple, right? Everyone knows merge sort. So let's just, for the sake of completion, because we spent so much time on finding ranks, the purpose was not that. The purpose was the next algorithm, the next problem that we want to solve. Merging is a very simple problem. We all try this thing. It's a divide and conquer strategy. We have to sort an array. We sort the left half. We sort the right half, right? We ask a friend to sort it for us, the left half. We ask another friend to sort the right half for us. And then we do the merging only. Merging is given on the previous slide. So it's a very, very simple algorithm, right? Unless the array is too small, in that case I don't need to divide. Every recursion, every recursive algorithm requires a sorting, stopping condition, right? This slide you must have seen in your discrete math course, right? This you must have seen in your tutorial on recurrence relations. They have done a tutorial on recurrence relations? Yes. They did recurrence? Okay. So you must have seen this recurrence relation also, okay, that it takes merge sort. The runtime of merge sort is T of n. Well, it requires merge sort on an array of the left array, the left half, which is n over 2 length, another merge sort on the right subarray, which is length n over 2. So that's Tn is going to be 2 times T of n over 2. Plus it requires merging of the left half, which is length n over 2, and the right half, which also is length n over 2. So the total runtime is twice or sum of those two lengths, which happens to be n, and that's going to be the basic recurrence if you're doing recursion. If your stopping condition, if you're at the base case, then it doesn't take, it only takes one comparison to sort the array of length 2. So if n is 2, then or less, then we just take one comparison. So if you sort this recurrence, it amounts to order n log n. Everyone knows it. You can prove it by induction. You can find the recursion tree. You can do the substitution method. You can do the master theorem. Many different methods to find this recurrence amounts to order n log n. Okay. So next I'm going to do one quick problem of counting inversion in an array. Okay, that's also, so hopefully I will be able to make the problem clear and some applications of that clear, and this will be okay. So I'm going to quickly define it. So please, and the slides will be uploaded right now, right after the lecture. So please go home and read that. You given an array A, right? We define, just like previously, we defined rank, right? There was not a problem, was not posed yet. I just defined something. So here I'm defining an inversion. Given in any array, an inversion is a pair of two indices, two locations, two spots in this array, which have the left number is bigger than this right number. The number at the left index is bigger than the number at the right index. Okay, so a pair of indices I, j, such that I is to the left of j and the number at I is bigger than the number at j. Okay, so in this array, this is an array of 8 elements. I'm going to give you all the inversions. Here is the index pair 1, 2 makes an inversion. Why is index pair 1, 2 make an inversion? Why does it make an inversion? Yes. Because the first condition is because 1 is less than 2, 1 is to the left of the 2, the index 2, and the number at 1, which is 51, is bigger than the number at index 2, which is 43. Okay? Can you give me one more inversion here in this array? Index 4 and 5, right? See, the bigger number 91 is to the left of the smaller number 22, right? Any other? 6 and 7, 75 is bigger, but it's to the left. It's out of order pair, right? We think of order as increasing order, ascending order, and now this is anything that looks out of order, anything that needs to be worked out, some swapping, some exchanges, that is called an inversion. Is this clear? It's very closely related to the sorting problem in the sortedness of an array. Here is some question you should ask yourself. How many inversions will be there in a sorted array? In a sorted array, how many out of ordered pairs will be there? Why? Because sortedness means every pair is in order, right? Any number that is to the left is smaller than any number that is to the right of it. Okay? So that's how you understand it. What is the maximum possible inversion in an array? Huh? Size of the array? What is the maximum possible number of inversion in an array? Okay, let's say, what is the minimum possible number of inversion in an array? Yeah, can you please talk to me? What is the minimum possible number of inversion in an array? Why 0? Please stop talking. Why 0?
Because they might all be in order or sorted.
What is all? All numbers?
All of the indices with each other, they will be sorted
All of the indices with
respect to each other or with
each other. All pairs of indices are in order, right? So what is the maximum possible number of inversions?
all the pairs. Like
Yes, what is the number?
n into n minus 1.
Okay, so you previously said n, I want to see. Maybe the maximum possible number of inversion is that all pairs are out of order. How many pairs can you make from n numbers? How many pairs can you make from n numbers? No. How many pairs? How many subsets of size 2 you can make from n numbers? N into n plus 1 over 2? You guys, how many of you got an A in discrete math? 2 power n? Wow. N times n minus 1? N choose 2. It's a key word. N choose 2. That's exactly the definition of the word. N choose 2. From n numbers, choose 2. Choose pairs. Choose subsets of size 2. So it's not going to be n into n minus 1. Its value is going to be n into n minus 1 divided by 2. That's the value of n choose 2. The definition, the concept of n choose 2 is finding subsets of size 2, right? So the number of pairs you can make from n items is n choose 2. Is this clear? So the maximum possible, this is the way you understand the concept, right? You find the max value, the minimum possible value, the extreme value. You just do a few examples to see, just like we saw in the previous one. So an inversion is made by two indices or the numbers at those two indices, right? Both are involved, both definitions are involved, both the indices have to have some order, some relation, and the numbers at those indices have to have some relation, right? So how many inversions will involve the number which is the min of the array A? Min of A. How many inversions the min of A will be involved in? How many inversions will involve the min of A? Let's say the min of A is at index 1. It's the first index. How many inversion will involve it?
I was thinking the rank.
The rank? No. Rank of min is always 0. Sorry, 0 inversions. What if the min is written at the last index? So why did you say 0? How many inversion will involve the min? N minus 1. So what is the min of this array? What's the min of this array? 22. How many inversions? How many min is at 5? So how many inversions here have the word 5 here, the number index 5? 1, 2, 3, 4. So understand the min. Now don't try to answer the question. Understand what is min, what is an inversion. An inversion is out of order pair. A min is out of order. Yes.
So it will be swapped with all the elements before it, so inversions existing.
Yes. If a min is at index 10, with the previous 9, it will make an inversion. If the min is at index 77, with the previous 76, it will make an inversion. If a min is at index first, one index, It with no other pair, with no other index will it make an inversion. Does it make sense? How many inversion will involve the max? Something like this, depending on how many numbers are to the left of, to the right of max, right? With every number to the right of x, it will make an inversion, right? Because this is bigger and those are smaller. This is the max, right? So to understand the concept of, a very simple concept, it's an inversion, just do this type of analysis, okay? And this is seriously an exercise in language. It's not an exercise in computer science or algorithms or math or anything. It's just a language. I just showed you a word, I gave you the definition, the got that thing into your vocabulary. Now can you identify it, right? It's simple pattern recognition, simple word understanding. So that will be an inversion. Now I want to give you one quick applications of this. So this the number of inversion is this basically, if an array is totally reverse sorted in decreasing order, let's say, then every pair will make an inversion, right? The definition that so there will be n choose 2 inversions. That's the maximum, the worst case for an array to be sorted, right? The farthest an array can be from sortedness is that every pair is out of order. Right? If an array has all pairs out of order except 1 or 2, we will say it's quite close to sortedness, right? It's easy to sort, right? If you do insertion sort, there will be only 2 swaps, right? In insertion sort, you must have seen that if there are fewer inversions, then it will, we didn't use the word inversion then, but there will be, if there are very few swapping needed, then insertion sort is quite good, right? So it's a measure of sortedness of an array. And that measure is used. So I'm going to give you one application. We did this is a huge applications of number of inversions. When you have voting, which is ranked choice voting, where people don't not only just choose one out of the multiple idiots, they just give a ranking of the candidates. Okay. So in that case, we do count inversion to find the best candidate or the winner or something. But the other is collaborative filtering. How many of you know recommenders or recommendation systems? Please, you have to give me 5 minutes, okay? Because in the first 5 minutes you came late. Generally, those of you who know me would know that I don't take any extra time. This Sharjeel is going to be not happy, but what do? I have to complete the number of minutes of talking about algorithms in this lecture. So because most of the time I was doing all the other nonsense. So let's see. What is the recommender? What is the recommendation system? Anyone who knows recommendation? Anyone? What is PYMK? Anybody heard of PYMK? Your Facebook emails you send people you might want to kill, people you might know type address, right? How many of you have seen on Amazon that you might also be interested in something like this, right? Every day you go to WhatsApp, it gives you, these are communities, these are people you might, every day you go to LinkedIn, it tells you these are the idiots you might want to connect with or other stuff, right? All of this is recommendation system, right? Why? Because these corporate leaders, they really want to serve humanity. So they really want to know this. Okay, we don't want to bother them by searching for items. We would rather find items and shove it down their throat, and they call it recommendation, right? So the search problem is a customer initiated thing. You go to a shop and you say, "Chacha, ye cheese hai," and they tell you yes or no, and then you buy it. But here it's the other way around, right? They want to force stuff onto you. So that is what's called recommendation. What are the things that you might be interested in? Who are the people you want to add on Facebook, right? Or who are the people, Twitter handles that you might want to follow, right? And every people does this. So TikTok has a really good recommendation system. Netflix is a really good recommendation system, right? The recommenders actually came from them. Actually, they worked a lot on Netflix. So one algorithm for recommendation is based on, so this is the idea of recommendation. This way too many products at places of scale of Amazon or Netflix or something, way too many products, way too many people. And there is very little demand for too many things, too many products have very little demand. We want to make demand for it, and that is where we want to find who will be interested in this, right? So this customization or personalization to individual users, here is how they do it. This is what the theoretically the problem is. You are given what's so-called rating matrix, utility matrix, where every row is a user, every column is a product, and think of it, suppose every element, every cell is actually the rating, the likelihood that this person will buy this product. The rating this person is given, the number of stars this person is given for this product, right? And so in this matrix, a lot of it is going to be empty because not many people give many reviews or ratings for many products. So there is going to be empty. We just pick on one empty cell and I want to predict what will be this user I's value ratings for product J. If that number happens to be big number in my estimation, I will send you tomorrow an email that this is the product you might want to buy, right? This is the movie you might want to watch. This is the friend, the person you might want to befriend in Facebook or something. So one of the things that we do in recommendation is called collaborative filtering. We see what is your watch history, what is your rating history, what is your like or thumbs up history for each product. If they are similar to your friend, the other people, then their choices are going to be recommended to you, right? So here is the idea. So I have U1, U2, U3, 3 users, and these are a lot of articles or books or whatever products. If I figured that U1 and U2 are very similar, then any movie that U1 watched, I will recommend to U2. Any movie that U2 watched and liked, I will recommend to U2. Anything that U2 didn't like, I will not recommend to U1, or vice versa, okay? But I also figured out that U2 and U3 are less similar. Their taste is different, their choices are different, their requirements are different. So whatever U3 does, it's not going to have any impact on U2, right? So in order to find a similarity, a metric, a distance or similarity between the users, one can use actually the number of inversions in the ratings of U1 and U2. So this is one slide I'm going to stop at. If you do the rating of U1, find the rating of U1, sort them, sort the products they like the most, in the second most liked product, the third most product, right? Bracketize arbitrarily. Sort the rating of U2 in that order, right? What is the rating of U1, U2 for the U1 most favorite product? What is the rating of U2 for the U1 second most favorite product? What's the rating of U2 for the U1's least favorite product? That in this array, the more there are inversions, the more U2 is dissimilar from U1. Okay, a concrete example is given there between U1, U2, and U3. You should see that. So next time we will continue with counting inversion. Finish. Most probably I won't be here. Counting inversion and then sorting lower bounds and integer sorting. Okay. Okay. Thank you very much.